Algebra II 4.6c, Algebra connects to geometry, 3 equations and 3 planes. If you haven't seen the previous videos 4.6a and b, you might get confused, so there's links in this video's description so you can watch them very quickly and then come back. When we have a system of 2 equations, it's graphed on a 2D plane. It's two-dimensional. We have 2 variables, x and y, and we just graph them on this plane, don't we? Well, the graph of an equation, ax plus by plus c is equals d, is a plane. 3 equations in x, y, and z represent planes in space. Just as 2 lines on a plane may be parallel, intersect at one point, or coincide, 3 planes in space can be related in several possible ways. And here's some of the ways the 3 planes can be related. So here's my cool little artboard I finished making, and it's the intersection of 3 planes. And if you remember this guy, I showed him in a couple of the videos. See him? It's 2 sheets of paper crisscrossing and then 1 bisecting it down the center. See? And it's not the straightest thing in the world, but it was not that easy to make either. Can you imagine having to make one of those every single time you had to do a system of 3 equations so that you could graph the answer? So that's why we use elimination and substitution. So for an intersection of 3 planes, we can have 3 sheets of paper that crisscross in the middle. See that? They all intersect in one line. That's consistent and dependent. These 3 sheets of paper are just laying on top of each other. The 3 planes coincide. And coincide means they occupy the same space. One is on the other. So it'd be like taking 3 sheets of school paper and just stacking them on top of each other and letting them lay on top of each other. For this one, there's the yellow one and the blue one laying on each other like they're stacked, but then the pink one's cutting through them. And then this one is this guy that I made. We've got crisscrossing sheets of paper and then 1 bisecting them. They all intersect at one point. It's consistent and independent. Here we've got 3 sheets of paper floating in the air, not touching each other. They're all parallel to each other. All 3 planes are parallel. In this one, the yellow and the blue one are laying on top of each other, and the pink one is hovering above them. And that's inconsistent and independent. 2 planes coincide, and the third is parallel to them. In this one, the pink one never touches the blue one, and the blue one never touches the pink one. But the yellow one touches both of them. 2 planes are parallel. The third intersects each of the others in a line, and that's inconsistent and independent. Now this one, this makes an infinite triangular prism. Each plane intersects with each one of the others, and you can see that the yellow one touches the blue one over here, but it touches the pink one way over there. It doesn't touch them together. It touches them separately, independently. See that? When a system of linear equations has one solution, the graph of the equations will intersect once, like right there. This system is consistent and the equations are independent. It means they're different lines. So it's like this line says, I'm going to the mall, and this line says, well, I'm going to go watch a movie. So they're going in 2 different directions. So they're independent of each other. When a system of linear equations has no solution, the graph of the equations will never intersect. They'll never cross. This is inconsistent. It's no solution. And they are independent. They're different lines. So independent means it makes different lines. See that? They never even spoke to each other. And they never will. They'll never cross and intersect each other. Well, when a system of linear equations has infinite solutions, the graphs of the equations intersect at all points. They're laying on top of each other. They make the same line. This system is consistent and the equations are dependent. They're the same line, so they're dependent on each other. So when it's dependent, it's the same line. When it's independent, it's a different line. That couldn't be too hard to remember, right? And look at this. If we were to take this system of 3 equations and we multiplied this by 4, this by 2, and left this one alone, we'd have the exact same equation, and they'd all be graphed on the same line. See? That's the slope. That's the y-axis intercept b right here. And if we multiplied that by 4 and that by 2, they'd all be y equals 8x plus 16. See? So a system of linear equations has infinite solutions. It's independent, like numbers 1, 2, and 3. See? These are all dependent. And if a system of linear equations has no solutions, it's inconsistent, like 5, 6, 7, and 8. These are all inconsistent. Well, 4 is not. 5, 6, 7, and 8 are inconsistent. See? These all have the papers touching and coinciding together. These have it so maybe 2 are touching, but not all 3 together. See? And that's what makes them inconsistent, because all 3 pieces of paper all 3 planes are not touching at exactly the same time. See, they're either not touching at all, or 2 are touching and 1's not, or 2 are touching and 1's not. See? All right, our next video is 4.7a. We're going to talk about linear inequalities in boundaries and half planes. I did this in Algebra I, and that was in video 9.5 and 9.6. We talked about inequalities in 2 variables and boundaries and half planes. We're going to do it again. And I'm going to add this video to the Algebra II playlist so you can catch up and review. All right? And one last thing I wanted to point out is when we see 3 variables, we know that makes an ordered triple now, don't we? That's 3 equations. Did you know that there's an ordered quadruple that has 4 variables, and that would be 4 equations? There's even an ordered quintuple that has 5 variables and 5 equations. And it goes on and on. You could have 8, 9, 10. And it's typical to have the x, y, z first, and then list the other variables afterwards. That T actually stands for time. Start getting into space-time when we're getting that many. Okay? You can go to Wikipedia and look up 4 dimensions and 5 dimensions and see what they look like. Okay? I think the 4-dimension Wikipedia one is really cool because it shows this shape turning inside out and everything. All right? Okay, we're going to move on and talk about boundaries and half planes. I hope this was enlightening. I hope you're doing okay. And remember, if you're confused, that means you got ahead of yourself, and you need to go back in this playlist to figure out what you lost, okay? All right, I'll see you next video. Bye.